Okay, welcome back to this afternoon session. Before we start, just to let you know, we put the AC in the room, so please don't open the windows and keep the door closed, otherwise it's totally useless. So, we can resume with our next speaker today, who is Carlo Heissenberg from Saclay. He's going to tell us about gravitational wave observables, PM expansion versus soft theorems.
Thanks, Laura. And let me start by thanking the organizers for the invitation. It's really a pleasure to be here. So the idea for this talk is to essentially go on and follow in the footsteps of Paolo, who already introduced a bit the topic this morning. So in recent years, there has been a series of developments that have to do with connections between ideas and methods derived from scattering amplitudes and, let's say, the scattering amplitudes framework more broadly, and that have been applied to this context of calculating gravitational wave observables. And in a sense, what I will try to do is to go a bit beyond what Paolo Di Vecchio already presented this morning in two directions, as we will see. One is to go a bit beyond the soft approximation concerning the waveform, and in the other direction is going to be to apply the soft theorem result that Paolo already introduced to calculate soft spectra. But more generally, I try to organize this presentation and discussion, in a sense, by illustrating two kinds of ideas that have been derived from amplitudes and have found applications in this context. One of them has to do with calculating observables in a sort of perturbative expansion, which now today has reached rather impressive orders in the so-called PM limit, which we will briefly review, but as you may remember from this morning, this is the regime in which the two objects stay far apart and interact weakly, so it's a weak coupling expansion. And the other is actually an idea that is very familiar to this audience, that has to do, instead of a property of the system, has to do with what we do. So we as observers have the right to focus on the low frequency band of the gravitational wave emissions, and in this regime, soft theorems apply, which in fact are very powerful in the other, as seen from the other perspective, in the sense that they do not rely on this weak coupling approximation. So this is mostly going to be based on recent works in collaboration with Alessandro Giorgudis and Rodolfo Russo, as well as with this paper with Francesco Alessio and Paolo Di Vecchia, and again for the several details and more introductory considerations that we'll inevitably skip. And let me refer you again to this review, together with Paolo Di Vecchia, Rodolfo Russo, and Gabriele Veneziano. And as I already emphasized this morning, please feel free to interrupt at any time and ask for clarifications and impose questions. We can make this as interactive as possible. So here is a schematic outline. Just to get everybody again on the same page, I will start with a few words of introduction and motivation, just to reiterate a bit the terminology, which especially for people who are not directly working in this field can get very confusing very quickly. So hopefully I will try to make again the point, and then introduce a bit the schematic ideas. Then essentially I will try to enlarge, as I mentioned, these connections between amplitudes and gravitational observables by coming back to an idea that Paul already mentioned this morning, which is the idea that looking at the amplitude is not enough in the standard perturbative way as we understand it. We have to find a structure that allows us to exponentiate it before taking the classical limit. This is the iconal exponentiation. And in this talk, we will explore a sort of generalization of this exponentiation, which more usually focuses on the 2-to-2 amplitude. And we will see how, what the proposal is to extend this exponentiation to turn it into an operator identity, which is supposed to include also the 2-to-3 amplitude, and in this way, the gravitational waveform. So this will allow us to calculate the waveform for our 2-to-2 process beyond the soft limit, but to first and subleading order in the PM expansion. And then I will switch gears a bit and go back to this set of results that several of you are familiar with, and Paolo also reviewed and extended a bit by going to all orders in these leading logs. And we will see essentially how we can use these results about soft theorems and plug them into formulae that tell us about the spectrum of radiated energy of the system and the loss of angular momentum, if time permits. Okay, so let me start, as I said, from the very basics, just to review a bit the terminology. So the problem that we are very interested in is in principle to state. We just send into massive with some mass M1 and M2 and see what happens. Now, this is very easy to state, but very hard to solve in practice, as often happens in life. So there can be two possible strategies one can come up with. One is to say, let's put the system on a computer, and this is the very important effort of numerical relativity, of course, which is crucial, especially to resolve the dynamics in late phases of a merger events when the two objects are very close together, and therefore the dynamics is highly nonlinear and is only amenable to numerical treatment. Instead, in this talk, as in Paolo's talk, the mindset is going to be a bit different. We will try to find a small parameter that we can expand in order to gain analytic control. So perhaps the most well-known and perhaps even specifically for observational purposes, the best approximation method period is the post-Newtonian one, in which one expands simultaneously for weak interaction. So when the size of the object is much smaller than the typical separation, and simultaneously small velocities, right? V much smaller than c. And so in a nutshell, this is an expansion for weak fields and slow motions. Instead, another approximation is going to play a key role in this talk, and in fact, as seen on revival, precisely due to this connection with amplitude that I will try to explain and extend, is the post-Minkowskian one, in which one only expands for weak gravitational interactions and at the same time keeps the velocity generic. I will come back to how generic this can be, also connecting with some observations that Paolo already mentioned this morning later on. So for the moment, let me sort of put an asterisk here, and we will come back to that. Then for completeness, let me mention another important limit that is sometimes very powerful and has also received a lot of attention, although today will not really play a key role in what we are going to discuss, which is the self-force expansion. So to leading order, the idea here is to consider a binary system in which one of the two bodies is much heavier than the other one, and then to leading order, this is a familiar setup that we also study in undergrad, in which the heavy object source is the geometry and the light object simply moves in the geodesics of the geometry produced by the heavy one. But this, so then people have devised a strategy, a systematic way of going beyond leading order in this so-called small mass ratio limit. And finally, yeah, the other protagonist sort of is going to be this soft limit, which in practice for bodies that move with typical velocities v and stay as a typical distance r means considering frequencies much smaller than v over r as suggested by dimensional analysis. Okay, so this is going to be the sort of playground, and what we're going to do is essentially to play around with this limit and with this limit and see what we can do in both cases, and in particular how one can inform the other and vice versa. So as I briefly mentioned, one of the key ideas lately has been to extract this post-Minkowskian dynamics from amplitude. So why is this reasonable? Well, the first reason is that amplitudes are already organized in terms of the powers of the coupling constant G, Newton constant, which is effectively also the power counting parameter of the PM expansion. So it's kind of reasonable that, say, from a leading order amplitude, you should be able to extract a leading post-Minkowskian or 1 PM, and so on and so forth. And in fact, this connection has been exploited and explored up to state of the art, which nowadays is this 5 PM, so for loop calculation on the amplitude side, which has been calculated at one self-force. So you already see here that as the problem becomes more and more complicated, people already think of, applying two types of approximation at the same time. So the idea here that has been used is to study the 5 PM, but not the full 5 PM, to begin with sticking to the leading order in this self-force. And now people are working on the 2SF, I think. And another idea that is sort of should make this plan plausible is that, okay, amplitudes are naturally Lorentz invariant, so they are more naturally connected to a regime in which velocities are kept generic instead of being expanded in the non-relativistic limit. And then finally, although I will not have many things to say, actually nothing to say about, but just for completeness purposes, let me mention that although we will study scattering events, some of the results and the mileage that we will gain by doing so can be exported also to the scenario of bound systems. So when the two objects do not simply interact and then fly off to infinity, but actually form closed orbits and eventually in spiral to a final object. Basically, the idea here is to make an ansatz for an effective potential that should describe the system both in the unbound and in the bound setup, then fix the ansatz that you made for the potential in the unbound case, and finally apply it to the bound case. Although this, of course, is a lot subtler than I'm describing right now. In particular, goes under. It has to go under an analytic continuation. It becomes more and more subtle the more you go on in this PM. Okay, so this is the sort of schematic idea for one of the two limits. What about the other one? So now forget everything I just said about the PM expansion, and let's look at the completely different corner of parameter space, which is the soft limit, right? So when we send the frequency omega to 0, the waveform becomes very simple to leading order, and in fact enjoys universal properties that have been shown in particular in this very nice set of papers by Sahu, Sen, and other collaborators. So in particular, the very leading order of the waveform is fixed to be a 1 over omega, and essentially this goes back to Weinberg, and the fact that this so this translates by Fourier transform in time domain to a memory effect, as was emphasized in a paper by Strominger and Zhiboydov. And so this is one, say, the first really universal constraint that all waveforms must satisfy. If in any other limit you calculate something, you take the small frequency limit, and it's 1 over omega piece does not match this thing, it means you've made a mistake. And now, I mean, the really new features of these papers here, what that similar universal results and universal simple forms are enjoyed also by some next to leading orders, subleading orders, in particular this coefficient of log omega. It also has a reasonably nice form. So PA, PB are the initial and final moment of the hard state. Instead, here we are looking at the soft radiation limit. And also the omega log omega squared has this relatively simple formula. Again, this provides a simple cross-check of any other calculation, for instance, and does not rely on the PM approximation. And the explicit form of this tau here depends a bit on what theory you're considering, in particular, how many massless mediators you might have. Here, for instance, it's the expression for general relativity. And as Paul already mentioned, this can be actually, in a sense, fixed by looking at what infrared divergences your theory has. So in this talk, we are essentially gonna go a bit to and fro from these in these two regimes, and so let me start from the first one. So in this PM regime, as we mentioned, maybe let me exploit this small piece of blackboard that I have here. We are just really sending the two massive objects in this way. They will interact. They will deflect a little bit. Let's say we send them in with some momenta P and minus P if we are in the center of mass frame, and some roughly some impact parameter B, which you could draw this way in a sort of democratic way, or if you prefer in this more standard version, let me call this BJ, perhaps. So this would really be the incoming impact parameter for the initial state. And then we are going to consider a regime in which the mass of these objects is very large, in the sense that each object is classical, meaning its mass is much bigger than the Planck mass. Or if you prefer, another way of stating this inequality is gm squared over h bar much bigger than 1. This is indeed very big if you plug in the values for astrophysical black holes, something of the order of 10 to the 79 or something like that. And also gm over b is going to be small in such a way that we stay in PM regime. So what Paolo talked about is how you can extract the deflection angle, so by how much the initial velocity is a deflection, is a rotation of the final one. And instead, my goal here is to discuss how you can extract information about a different observable, which is not really a property just of the massive objects, but really of the gravitational radiation that is emitted by these guys. So this thing, which is what we measure, we would measure at LIGO and Virgo in the presence of one such scattering event rather than a merger. So in order to do that, instead of focusing on a 2-to-2 amplitude, which is what appeared in, well, was sort of the protagonist of the first half of Paolo's talk, I'm going to consider this 2-to-3 amplitude. So as you can see, compared to what you saw this morning, there are not only the initial and final, let's say, thick lines which represent the massive states, so the two objects going in and then coming out, emerging from the interaction, but also the emission of an additional graviton. My job, the first half of the presentation, is to explain what do we do to this guy in order to obtain this waveform. So in addition to the Mandelstam invariants S and T, which are roughly related to the momentum transfer and to the total energy present in the process, which for historical reasons we are characterizing as Q, the momentum transfers, and sigma, although many people would call this gamma. This is nothing but the relative Lorentz factor of particle 1 as seen from the rest frame of particle 2, or vice versa. Here there are also the frequency of the graviton as seen from particle 1 and particle 2, and a bit of a difference with respect to this morning is now you have two momentum transfer, right? Because the momentum lost by particle 1 is not all gained by particle 2, it can also be emitted a bit via the emission of this graviton, so the momentum conservation condition is this one, right? Q1 plus Q2 is equal to minus K if you want. And then finally, here and there might appear this alpha. Alpha are very much related to this omega 1 and 2. They are simply those guys rescaled by the frequency as defined in the center of mass frame. So E and omega are the total energy of the process and the frequency of the graviton as seen from the center of mass frame. Okay, so before spoiling the result, says telling you exactly what to do, let me describe a bit the structure of this object here, right? So you remember schematically what happened in the case of the one loop on the 222 amplitude, which I think Paolo was calling A. The idea was to consider it as a function of impact parameters, so to this tilde representation, and then the nice feature was that it was in this, precisely in this limit here, the amplitude is dominated by this exponential here. And to leading and subleading order, this equality was fixing the value of the leading order of the phase and the subleading order of the phase in this way. Okay, so from this, sorry, delta 1, which would be the subleading order. So the logic is from the 3-level amplitude, you can simply deduce the 3-level, the leading order contribution to this phase, and then from the subleading amplitude, there is some garbage that you have to subtract. Okay, if this garbage is not there, it also means that you made a mistake. You have to first subtract it, and then you find this guy here, which is the next to leading order correction to this. And so let me discuss instead how this works for the 2-3 instead of the 2-2, which is there. So again, the 2-3 at leading order is some 3-level amplitude. Unfortunately, compared to Paolo's talk, I will not be able to really show many explicit expressions for these objects because they are a bit longer, but they are all in the ancillary files of the papers that I'm citing here and there in the slides. So you should think that this A0 is a relatively simple object. You just, in principle, you can even calculate it just with Feynman rules. There's some rational function of P1, P2, Q1, Q2. And then the one loop is a bit more interesting. As predicted by unitarity, it has both a real part and an imaginary part. So this, of course, already appeared in this 2-2 amplitude that Paolo had, and in particular, this imaginary part corresponded to a unitarity cut that had this form. So it was just the iteration of the 2-2 at one lower loop. Here instead, I have a few more unitarity cuts that fix the imaginary part via the usual optical theorem or generalized optical theorem, right? There are indeed some two particle channels, this one and this one, which are essentially the analog of these ones that appeared this morning, but with an additional graviton here or there. And then there are some genuinely new beasts, which instead, as you can see, involve an intermediate subprocess in which the graviton is first emitted and then rescatters against the curvature of either of the massive objects. So you see the sub-amplitude here is sort of the analog of a Compton process, right, in electromagnetism, in which you could imagine that a photon scatters off an electron. Well, here is the gravitational analog of that. So for this reason, sometimes we refer to them as Compton channels. And now, let me, again, in analogy with what we tried and succeeded in doing in the 2-2 case, the idea is to try to match this to a more complete exponential ansatz. So instead of trying to make the ansatz that the amplitude, or more precisely the S matrix, is really just a phase for this process, we try to include also gravitational radiation in the following way, right? So you remember the idea in this exponentiation is that these graviton exchanges that are mediated in this kind of 2-2 blobs exponentiate because they're all statistically independent. It's essentially as if you were exchanging a coherent state of gravitons, which builds the gravitational interactions and therefore the deflection. So here, to first approximation, the idea is to make an ansatz in which both the exchanges and the emissions are correlated. uncorrelated, and therefore the idea is to promote to an exponential both this phase here, which characterizes the deflection, and a piece here that involves operators, so annihilation and creator operators of the graviton, which instead build the gravitational radiation emitted in this way. So coherent exchanges and coherent emissions. This is a bit the slogan. And then the idea is that you can test this to order by order in perturbation theory, right? Like we said earlier, suppose this Hanset had not been correct in the 222 case, what we would have found is that we wouldn't have found this guy, right? The first check of the exponentiation. This Are we going to explode? I hope not. Okay, the idea is that we're going to do exactly the same here. What we can do is try to use this to match instead of this 5-point amplitude. From it, we can deduce both delta and W now, which is our new ingredient. And then, okay, I will not do it here. It's very similar to this. You, instead of matching to the 222 amplitude, replace this here by A5, this 223 amplitude. And what happens here is that basically you pull down W from this exponential instead of pulling down delta. Okay, imagine we have done that. So I will come back to what the outcome of this is in the next slide. But first I wanted to emphasize why this is useful. So the first issue that we solve by promoting the iconal from this guy to that more complicated guy is that we restore manifest unitarity, right? Earlier, you remember in Paolo's talk, there appeared at some point an imaginary part in this delta. And this means that the probability amplitude that this process happens was suppressed, right? Because if this delta develops an imaginary part, you will get a suppression. In fact, an infinite suppression strictly in equal 4, right? Because there was an infrared divergence. So it means that this guy, as d tends to 4, is tending to 0. So we are not looking at a very likely process to happen. It's actually better to do something like this. And the reason is that, I mean, okay, the way I'm writing it's kind of obvious, right? Since this is a Hermitian operator, then the norm of the final state is exactly the same as the initial state. So now, at least the out state has probability norm 1. Yeah, so exactly, thanks. So compared to this model, there was also a similar thing that appeared maybe at some point, but there the idea was to focus just on some small k. Okay, here the proposal is really try to, to promote this to a coherent state emissions for all k, and see if that's consistent order by order in this PM expansion. I will come back to later if this is a good idea or not, and maybe we have to do something more, but at least, okay, the bottom line is that at the first 2 orders in perturbation theory, this seems to be perfectly okay, even beyond the small frequency limit, exactly. So then the second thing that, okay, this is nice, but what do we gain in practice? Well, we gain that now we have a more complete description of the final state, and we can use it to calculate more general observables, in particular observables that have to do with this radiation here. So in particular, we can use the idea that was introduced in this context by Kosower, maybe, and O'Connell. We can use this out state to calculate an expectation value of any operator that we like, in particular, the canonically quantized graviton operator. And this will give us a prediction for the waveform, which, not surprisingly, is exactly this W over here. So bottom line, instead of starting from the 222 amplitude, taking the Fourier transform, matching to the iconal and getting the deflection, the pipeline is calculate the 223 amplitude, match to the operator version of the iconal, calculate W, get the waveform, and then you're happy. So let me explain what happens when you try to do this at 3 level and at 1 loop. So at 3 level, as you can imagine, there is nothing much that happens, exactly in the same way as this is the leading order iconal. W is just the 2 to 3 3-level amplitude, 3 level, which is, as I said, a relatively simple rational function that was first calculated in this paper here. Now, what happens at 1 loop, again, let me try to sell it to you in analogy with what happens here. As you can see in the 222 case, what happens when going from the amplitude to the iconal is that some cuts, some things that are fixed by unitarity, simply drop, and you have to just retain this guy over here. Here, the same happens, but what you have to drop are these 2 S and S prime cuts. So only the ones that are, well, that you can think of as intermediate, processes in which the intermediate state is a 2-particle state, a 2 massive particle state. Instead, you have to keep this C1 and C2. So basically, from this one, you have to erase this term over here. So this is the result. And disclaimer, which is actually seems like a subtlety, but is very important. This is correct, provided that once you do the Fourier transform, you interpret the variables not that is P and Bj, but rather as B and let me call it maybe P tilde. which are sort of democratic with respect to the incoming and final state. Otherwise, as the figure suggests, if you are using less symmetric variables as reference vectors, well, you can still write down the answer, but it will still include some more complicated pieces. Particularly, it will include this term with a minus sign here instead of just canceling it. The reason why this is important only next to leading order is that, as you can see from the figure, the difference between P and P tilde or B and Bj is of order theta, right? Or more precisely, it's a rotation by theta over 2. Easy trigonometry exercise for you when you go home. And therefore, at leading order, it doesn't matter because theta is small and of order G, but here we are trying to do things that are next to leading order in G, so okay, it matters if you use a different variable which differs by the other one by an order G contribution. Okay, with this out of the way, this is the prescription that comes out from this iconal story. Take the amplitude and remove this two-particle intermediate cut. Two-particle with the intermediate massive particles. Okay, so now the challenge is, without showing explicit expressions which are very ugly, try to give you a feeling of the structure of this next to leading correction to the waveform is. So let me try to do that. So this B1 is the real part. And in a sense, it's what is associated to, in a sense, it's a bit easier, but this is a bit, let's say, not a very objective property. What do I mean by easier? So it has a piece which is actually a one loop calculation. In analogy, again, with the 2-2-2 case, it involves, in particular, some square roots, say, of Q1 squared and its friend. So you see, these are generally one loop things, right? You would never find a square root at tree level. But then it also has an even simpler part, which is due precisely to the same phenomenon that also appeared this morning in Pilo's talk when he was discussing the 3 p.m. deflection. There is a piece in this real part that is fixed in a simple way by a piece of this imaginary part, because the imaginary part is fixed by unitarity, and it comes with a log, and the log must come with an I pi, and the I pi multiplied by I over 2 is actually a piece of the real part. And this piece is this guy over here. So as you can see, it seems to be a one loop thing in the way I presented it, but it's actually proportional to the 3-level amplitude, okay, multiplied by pi g e omega. And to get this factor, you have to go through exactly the same exercise that Carlo showed. You can just write this this Compton cut over here, and then you realize that it has an infrared divergence. The infrared divergence comes with a log of the invariant that flows in this bubble, and all the structure is exactly the same. Okay, now these other guys, as I said, are a bit more complicated, and the reason for that, well, is that they have this integral over the intermediate phase space of the graviton, and the resulting structure involves in particular some logs, say some logs of Q1 over Q2, and some even more complicated logs involving omega 1 and omega 2, just to give you an idea really of the structure very, very schematically. But the point I want to focus on is that they have an infrared divergence. So why am I giving you an expression for an observable, the waveform, which is infrared divergence? I'm doing something not very sensible, it seems. So the way in which we can handle this, and in fact this had been already realized quite some time ago in the context of PN calculation, is that there is a nice interplay between the way in which this W appears in our expression for the observable and the infrared divergence, which, as we know, for instance, from Weinberg's pioneering paper, all exponentiate. So the infrared divergence, here is the famous log I was mentioning, right? From this cut here, say, there is an infrared divergence that comes with a log. But for the moment, let me focus really on this 1 over epsilon. What do we do with that? Since this is proportional to the 3-level amplitude, we can rewrite the full 3-level plus 1 loop in this way by exponentiating, right? This 1 over epsilon at the order in G in which we are working. And then we can reabsorb this e to the minus I over epsilon G omega by redefining the origin of the retarded time, this u that appears in the Fourier transform here, right? So this is the time domain waveform. And so it's something that depends on the retarded time and the angles at which it is observed. And if you shift u to u plus a constant, you will see that you can change this factor here, right? In particular, you can choose it to cancel this 1 over epsilon thing. Of course, this is a formal operation. It's a sort of renormalization, right? So in practice, this means that the procedure we are using we can hide away this infrared divergence, but then we have an ambiguity, which is that we can still perform finite redefinitions, right, shifts of this U. So another way of saying this is that we have an ambiguity under time translations. We simply don't know when the signal will arrive at the observer. We know its shape, it's this Fourier transform, or it's only defined up to a time translation. So we know the form of the wave form, but not exactly the time of arrival. And okay, this has in practice no consequence, right, for our colleagues, because, well, they don't know when an amplitude and a gravitational wave is supposed to arrive. They just wait and then fix experimentally the time at which it arrives. So maybe one last comment before moving on is that, so to summarize what the structure in this guy is the following. There are some integer Pn, or even in velocity, or conservative, let's say, or instantaneous. These are all essentially synonyms in the literature that come from A0. So A0 is the 3-level amplitude, and if you want, you can think of it as resumming all the corrections to the Einstein quadruple at leading order in G, all the corrections in the velocity, which are even in the velocity. And then there are further corrections even in the velocity that come from this B1, except the radiation reaction bit. And then all the odd corrections in the velocity start at the next order in G, so they are really in the one loop piece of this waveform, and they are either contained in B, so in this radiation reaction piece, or in the Compton cuts, these guys over here, after you subtract this, this infrared divergence in this way. Okay, questions about this sort of lightning presentation of the next leading waveform? It's a bit, I understand it's a bit, for people that like to see formula, it's a bit dissatisfying, because otherwise I would have spent 5 slides just to show you all the ancillary file, but this is what it is. I assure you we have very concrete representations of this W in the ancillary files of the papers here. Now, at this point, there is still one piece which is missing in order to claim that we really have an expression which is completely explicit for this next leading waveform, which is hidden in this tilde here. So you remember, to go from the momentum space to the impact parameter representation, we have to perform a Fourier transform. This is actually completely trivial in the 222 case, but these Fourier transforms are very challenging for this object because it's very complicated. So in the remaining of the presentation, let me instead come back to the issue I was mentioning at the beginning and show it in a simplifying regime, which is the soft limit. So the idea is, before performing this Fourier transform, you go to the soft limit, and then the expression simplifies, and you gain 2 things. One is that you can actually perform the Fourier transforms and get the final result in an explicit form, and the second thing is that you can compare with soft theorems. So we do that. We did that for the well, in the paper it is conveniently hidden by this zoom part of the interface. We did that with Rodolfo and Alessandro, and indeed we find that after performing the Fourier transforms, the result is in perfect agreement with the Sahu-Sen result. So this is the Weinberg scale, 1 over omega, and this is the log omega and omega log omega squared after you re-expand them for small deflections, right? Because as we said, there are 2 complementary regimes. We take our leading subleading PN calculation and expand this for more frequency. We take the general soft theorem, which is valid for small frequency. We expand it for small deflection, and then we find perfect agreement. And then we can go beyond that and calculate, for instance, the first few pieces that are not fixed by the leading and subleading soft theorems. So for instance, this omega to the 0 piece of the 3-level, as you can see, it depends on this alpha 1, alpha 2, or omega 1 and omega 2, this sigma, and here G1 and P are some polynomials that I'm not showing in order not to clutter up too much the slides. So this is just to give, the message is you can go beyond the soft approximation, but to first and subleading order in the deflection, so in the PM regime. And these are new predictions, if you want, that come from the amplitude. Now, there is one more feature that has been sort of interesting for us, and especially in comparing these results with what had been obtained in the literature. So there are yet another set of results that have to do with the idea of really sitting down and solving the Einstein equations and the equations for the motions of the bodies order by order in the PM expansion, but without ever mentioning amplitudes at all. This is a systematic framework that is in fact also used in the PN literature that goes under the name of multipolar post-Minkowskian formalism. So this is really, the hardcore way of solving the equation order by order in G, in the classical setup. And people had started comparing already this result of this MPM with the small velocity approximation of our PM result obtained from amplitude, and we're seeing something that did really quite match. So there was agreement in the first few orders in the velocity expansion, but then at some point at this 2.5 PM there was a disagreement. And okay, what we noticed is that the difference was a BMS supertranslation. So what had happened is that for historical reasons, the MPM calculation had been all performed in a frame, in a BMS frame, in which the shear in the far past is fixed by the in terms of the velocities of the incoming particles. Instead, in the amplitude one was performed in another frame in which the initial value of the shear is 0. So this was already been pointed out, in fact, in a different context by Veneziano and Vilkovisky, and we noted that indeed, putting the two calculations in the same frame, they indeed were agreeing. So this was a nice sort of twist of the story. And the first order at which it appeared is this omega log omega piece, which is not fixed by the general Sen-Sahu story. The intuitive idea as to why this is the case is that since the structure is something of the type 1 over omega plus log omega plus other things, and the supertranslation acts with a shift, right, with an inhomogeneous part that does not depend on time, so it's a delta of omega, let's disregard that, and then it also shifts the retarded time, right? So when you re-expand this piece, you will pick down, will bring down a power of omega that can cancel this omega or can multiply the log omega by omega, but can never generate something of the form omega log omega squared, for instance. So this is why we had to go to the first non-universal term in order to see this effect. And then, okay, let me cut the story short. After that, we also performed the comparison more generally beyond the soft limit, but to leading, well, in the PN limit instead, and eventually everything agrees with everything, provided that we take care of this subtlety of the BMS translation, super translation, sorry. And this was also cross-checked and expanded upon in a sort of different perspective also in this paper here by Bini and collaborators. Okay, so now concerning this next to leading order waveform, everybody agrees with everybody. Let's move on and come back to the other idea I was mentioning at the beginning. So this is the idea here is very simple, so I will explain it very quickly and then leave time for more discussion and questions if there are. Maybe I can give more detail if otherwise. So the idea is, since we have these general features of the waveform that we can access in the low frequency regime, but that do not depend on the PM expansion, sorry if I keep repeating myself, this is somehow one of the main messages, we can use them to plug them in formulas that give the total radiated energy and total emitted angular momentum. Here this slide is a bit scary because there are many symbols, but the important bit is just this contribution here. As you can see, the contribution to the energy radiated, if you cut off the frequency integral at some order, so you just focus on the spectrum, right? As you can see, since each of these W's goes like 1 over omega due to Weinberg, the leading order contribution to the spectrum is a zero frequency limit, which is finite, right? 1 over omega times 1 over omega times omega squared. And in particular, you can get a prediction for that zero frequency limit, which looks like this, which is a non-perturbative function of the incoming and final momenta. So the benefit here is that, since again this does not rely on the PM approximation, we can go back to the issue of the high energy limit that Paolo also already mentioned. So we can compare what happens if we first take the small momentum transfer limit, or if you want the large mass limit and then the high energy limit, with what happens if we do the opposite. If we first take the small mass limit and then take the small deflection limit. So the bottom line is that you try to do the first thing, you first expand in the usual PM limit and then take the mass to 0, you find a divergence. So the leading order in the PM expansion is order G cube. And then there is this calligraphic I function that also Paolo had and then contained the log of sigma. And the log of sigma is infinite in the ultra-relativistic limit. You can check that if you trust this leading PM approximation, this would seem to predict for you that you will radiate an infinite amount of energy, even just due to soft frequency gravitons, which is not really sensible. But here, the control that we gain thanks to the soft theorem tells you a different story. So if you first expand for small masses and then in the small frequency, in the small deflection limit, you see that the result is indeed G cube. So theta and Q scale with G in the same way. They scale like G, right? They are order G deflections. But then there is a logarithm, not of infinity, but of theta. So you can see that the issue here is that by focusing on the PM expansion, sometimes in some observables, you will have some observables that do not depend in G, like a power law or like a power series. And then, of course, if you try to, to calculate the Taylor expansion of something when in a point where it does not have a Taylor expansion, you will simply find infinity. But it means that actually the result is non-analytic in the coupling. So it's G cube log G. So this is, we believe it's a sort of hint as to maybe why this 4 PM result seems to be infinite in the large energy limit. Maybe it's because the result is actually a bit subtler, even in the massless case. And then, okay, I had several more slides we can come back to if you want during the discussion. Why? So here I was, well, implicitly neglecting what we call the nonlinear memory effect. There are ways to take that into account, and also similar story can be discussed for the angular momentum, but essentially the idea is very similar. Maybe one last thing before concluding and leaving the floor for more discussion. Coming back to this all order in logs, let's say, result that Paolo already presented. You can also put that one into the soft spectrum. Nothing is stopping you from doing that. And in fact, it's very easy to do that. And the reason is that these non-perturbative exponentials that dress the 1 over omega here do not depend on the angles. So the integrals that you have to do in order to go from here, you see this is an angular integral to here. Okay, the formula is, the calculation is exactly the same, since you have to keep track of this factor that is around, but which is completely inert under the integration. So the result generalizes the zero frequency limit to all orders in the omega log omega expansion. In particular, then you can re-expand that thing to leading and subleading PM orders, and sorry, this is the formula I wanted to look at. So you see, this is, for instance, the leading order resummation to all orders in G which bear this form. Don't make me read it out loud, but okay, this is the structure that it predicts to all orders in perturbation theory, as you can see, right? G to the n with any n. And moreover, you can again study the systematics by going first in the small deflection limit and then in the small mass limit, or vice versa, and you essentially will find an alternating pattern. There is a leading order which involves this calligraphic I, which is infinite, seemingly infinite, meaning that there is actually a log in the true limit, in the true ultrarelativistic limit, and vice versa, this calligraphic H, which looks a bit ugly. Okay, that one also instead has a nice high energy limit, so we will find that the structure alternates. There is a leading order which is, well, ill-defined because it has a log, and a subleading order which is actually perfectly smooth because it doesn't have a log. So if there is a lesson to be gained here, I'm not entirely sure, but it seems to be that logs are bad. Okay, so maybe in view of leaving time for further questions, this is a bit the material I had in mind. The presentation, there is a very similar story from the angular momentum, but yeah, maybe we can come back to that later if there is interest. So to summarize, so the two main messages that in the PM expansion, the idea is to promote this 2-to-2 iconal to an operator version, in which this operator, which this exponential becomes an operator. And to leading order, the idea is to just assume an coherent ansatz even beyond small frequencies. This seems to work well, at least to leading and subleading order in perturbation theory. So for small g. And the other message is that there is a complementary approach that we are all familiar with, in a sense, that also comes from amplitude, but in a different context, which are soft theorems, and these allow us to come up with via simple calculations. I mean, by the way, these integrals here I was showing, instead of these loop calculations that I was showing in the first half, all the integrals that are needed for these soft theorem calculations, you can do them by hand on some page. Of course, the price to pay is that they only encode the properties of radiation or radiation for small frequencies. And but they provide nice, cross checks and generalizations of the PM results. So maybe a few words about the future directions. Okay, one of course the problem that is left that we have to tackle somehow is to really derive this exponentiated form of the soft theorem. We have a sort of argument that is based on infrared divergences. Sorry, this guy over here. And we have proofs in several limits, in particular the leading order in the frequency, and independently this has been checked and derived to leading order in the mass ratio, but it would be nice to have a general proof. Moreover, I think it's important to try to understand if we need to go beyond this coherent ansatz. I think preliminary results at the next order in G for this two-loop waveform seem to suggest that maybe there is something to be understood there. Okay, this point let me skip it because I didn't really present it in the end. It's not a problem. Just to complete the spectrum of possible things that you can do, you can also integrate, right? Instead of calculating just the spectrum of energy and radiated angular momentum, you calculate the full radiated energy, the full angular momentum. This has been achieved up to order g to the fourth, but there is a piece missing, which is this guy here. And yeah, maybe it would be interesting to have a more concrete handle of the nonlinear memory effect, also coming from the amplitude perspective. So yeah, thank you for your.
Thank you. Are there questions from the audience?
Yeah.
Yes.
So you mentioned that like some of these calculations, like in order to get agreement, you need to fix a particular super translation frame. So these have to do with like actual scattering observables. Is there a preferred choice of super translation frame that do we know what that is?
Yeah, exactly. So I think this is a very important question. Unfortunately, at the moment, I don't think there is any concrete way, or at least we have been trying to think and discussing also with other colleagues, but I don't think there is really a clear answer to that question at the moment. I think, so the main thing you could ask is there a way of measuring an angular dependent time translation, right? This is the basic question. So this would require you to compare two gravitational wave signals that are received at the same time, in some sense, at two different angular separations with respect to a given source, right? If you see that you have, synchronize your clock with your colleague and you then let him or her go some, I don't know how many light years away in some direction, then you receive the signal at two different times, it means that there is a super translation background, right, in some sense. So the problem is that at the moment we cannot do that because our, LIGO and Virgo are just separated by, by the Atlantic Ocean, and that's not enough for any source to be at any meaningful angular separation with respect to us. And unfortunately, even LISA, who is planned to orbit, following the Earth around the Sun, that's not going to be enough for any of the sources that we have. If you take the ratio between, the distance between LISA at this time of the year and in 6 months divided by the distance from the effective distance from the source, this would be too small to measure. Of course, you could still try to ask. In fact, there was a very nice workshop at CERN a few weeks ago, and for instance, Donald O'Connell was, provocatively saying, suppose there is an extremely advanced civilization that manages to cover the whole celestial sphere and then communicate in some way, then can you or can you not? I think this is still a bit under debate in the following sense, namely that it seems to really have to do with the fact that super translations are really symmetries in this way of performing the calculations because we work to leading order in this 1/r approximation, right? And therefore, no matter how small the angular separation that you start moving in is close to the source, if you really travel to infinity, quote unquote, you will end up in two causally separated places in the celestial sphere, and therefore there is no meaningful way in which the two observers can compare their clock, right? Simply because you cannot communicate with one another. So maybe this, I don't know, it seems to suggest that maybe this has to do with relying on the leading order of the 1/r approximation of the waveform. Maybe we need to calculate the next one in order to sort of resolve this ambiguity. Another interesting point, although again, for the moment this is not really something very concrete, has to do with this infrared divergence, right? Because we know from examples like in the non-relativistic, this infrared divergence here, right? This is basically due to the fact that we are still always working with the retarded time as defined by the background. Okay, we know that, for instance, by solving the Schwarzschild case exactly, you have to perform a change when going asymptotically, right, using the tortoise coordinate, and that contains a log, and logs are bad. So this is the reason why we have an infrared divergence, is that because the true calculation would involve probably a log G of Gm over B, but perturbation theory just gives us infinity. So these two seem kind of vaguely related, right? One is a time translation, the other is a super translation. They appear exactly in the same part of the result, by the way. I didn't mention that, but the time translation changes this eliminates this 1/epsilon, and then this shifts this log mu. And instead, what the super translation does is that it multiplies this thing by a factor of 2. But they really appear in the same part of the result, which seems to have to do with... Maybe a preliminary question would be, can we even measure a translation? maybe it's an intermediate thing. Actually, people are very smart, more than me, and they've already thought about that. Unfortunately, the answer seems to be no, again, because of this, hierarchy of scales, but, maybe it's worth keeping thinking about that. Yeah, David.
Yeah, there, David Nichols. While the microphone is reaching David, can I ask if you could expand on the limitation of this coherent ansatz?
So this is very much sort of in progress, and with thinking about. In fact, I was planning to maybe ask Paolo in one of our free time. So it seems that one thing that of course, what we assume by this is that gravitational radiation is completely uncorrelated, right? At some other information theory, radiation should start remembering that if too much radiation has been emitted, well, you cannot still emit an infinite amount of radiation, right? There must be a correlation, even just induced by conservation of total momentum, right? Suppose that, so in other words, the reason why in the seminal paper by Weinberg, he shows that emissions are completely uncorrelated because he's focusing on the leading. No matter how many you have already emitted, since they are soft, as if they hadn't carried away any sizable portion of. But here, precisely because we want to go beyond the soft approximation, so we can also emit hard gravitons. Well, hard gravitons can carry away a sizable amount of the total energy of the process, and I think this has to do with this nonlinear memory effect. So, because soft gravitons can be then emitted by hard gravitons. So, my guess is that this might have some come back biting us in the tail when we do the next reading order, because it's the first one sensitive to the nonlinear memory effect. But this is a bit preliminary at the moment. Yeah, I think David had a question.
Yeah, so the question I had was about your comparison with the multipolar post-Minkowski.
Yeah.
I mean, so it looked like you just had the instantaneous nonlinear terms, so you didn't have anything involving a memory type term. And in the standard MPM formalism, right, you get memory at order g squared. You have this memory integral. So I don't exactly understand why this doesn't appear in the amplitudes perspective. You're saying you have to go to one order higher, which I assume means g cubed, right?
Do you mean linear memory or non-linear memory?
Non-linear memory.
No, it appears at order g cube.
But in the standard multipolar post-Minkowski, it's order g squared, right? So what is it that is g cubed? I guess I'm kind of confused about the counting.
Okay, there are two possible sources of extra g's. So what is your leading order in g?
Leading order in g is the waveform.
No, but here is just the waveform, and then we are approximating the waveform itself order by order in g. So the leading order of this waveform, in the way it's normalized in this equation, it would be of order g, and this is the first one, the first order at which it depends on time, and then yes, the statement is that with respect to this leading order here, which would be, for instance, the leading order of, let's say, the Einstein one, if you expand it to leading order in g, then on top of that you need two more powers in g in order to see nonlinear memory. Yes. This is for the scattering, at least.
Is this something specific to scattering? Because in bound
yes, it is. Yeah, no. For the bound, yes. For the bound case, it appears much earlier, yes.
Yeah.
Because I think there is an enhancement, in particular for quasi-circular orbits, it's sort of built up. Instead, here it's a very tiny effect, right? Because you first need to radiate. You have a radiation which already costs you some powers of g, and then on top of that, you add the Weinberg factor, if you want, the linear Vischer potential of these gravitons that involves another power of g, roughly.
Yeah, I mean, because in bound systems, if you have a binary...
Yes, thanks for the comment.
Like, I talk about Newtonian order, but it's the same order as...
Sure, exactly. For instance, in the PN counting, this does not appear in Newtonian order at all. This is highly sublinear. I think it's probably 2.5 or something like that. Okay. Yeah. Thanks for the clarification.
Right,
So unfortunately, this is somehow theoretically very exciting for us, but observationally not very exciting for our colleagues, as you can see, because they are a bit disappointed, because it's a tiny effect, scatterings.
And can you... So at CERN also there was this recent works about radiation reaction from in-bound to bound system. Is there a hope of connecting with those things?
I'm not sure I remember that specific.
Okay, maybe you were not there.
No, okay, so there have been several works. Yeah. Okay, coming back to this.
Yeah, I think they managed to compute exact radiation reaction, at least for some ratio between black holes masses. I'm not sure I recall the details.
Okay.
You
Now,
see what
now
I
I
mean?
remember.
Okay.
Now
okay.
I remember what you mean. So yeah, exactly. So the idea is that you need a principle that allows you to perform this analytic continuation, which is not the effective potential, right? Because the effective potential is intrinsically conservative. So if you want to start a radiation reaction, even try to continue the waveform, something else. Okay, something else. I really haven't studied the details of these recent papers by Cha-Shen Shen and other collaborators. But the idea is that they use a different. So they start by looking at this bound to unbound to bound map in a limit, in the limit of small mass ratio, and there you have more power. For instance, maybe I can briefly expand on this. For instance, the way in which this paper managed to really prove the omega log omega resummation, right? Also there, it's a complicated problem, but maybe you can start from a limit. There, the limit can be either the small velocity or the small mass ratio. And the reason is there you have this Tucholsky equation that also Paolo, I think, was briefly. It means essentially solving the problem in the case in which one of the two objects is much heavier, and then you basically calculate, let's say, roughly speaking, the propagator on the background of this guy and insert the light object. So I think the method that people were discussing in these recent papers was, it seems a bit more roundabout, but they say it works better, and they were also surprised, if I remember correctly, is that instead of doing that, consider a quantum version of that, in which you still model even these heavy objects as fields, and then you take the iconal limit, which is the regime in which these fields behave as particles. And but still in the regime of mass ratio, of small mass ratio. So I don't know exactly which equation of this formalism, but that was what was providing the bridge from the unbound to bound for them. It was what I got from that. It was sort of the analog of this effective potential. It's something that you can define both for the unbound and for the bound, at least in this limit, and then you can export from one to the other. Although, I'm not really the right person to comment on the details at the moment. Yeah.
Yes, another question. Yeah, we have still a couple of minutes. So.
Yeah, so I guess a related question. So for example, these systems will radiate linear momentum, so the center of mass frame will change. Is this also an order G-cubed effect here or no?
Yeah, okay, so linear momentum, okay. No, yes, it's a G-cube effect, exactly. It has to do, so the idea, well, maybe you can, the idea is that in this equation here, so this equation is the equation for the total radiated energy momentum, and then this rho is basically the square of the waveform with some star. So for us, the leading order waveform scales as g to the 3/2 in this normalization here. So you immediately see from this that this scales like g to the 3, right? Because this is quadratic. And so it's at the same order as the energy radiated. There is a nice symmetry property. At leading order in G, momentum will be only radiated in the direction of this P tilde and not in the direction along B. So the system will be dragged in the direction of the guy that is heavier. Will start moving if you place the center of mass initially at rest. It will start moving in the direction of the heavier guy, but it will not, let's say, be pulled in one of these, in either of these vertical directions. So this is a feature of the amplitude. I mean, this is easier to see from the amplitude because there is a symmetry under B that goes to minus B essentially. And then at the next order, there can be also an effect due to this Compton cut, so basically to rescattering or to the tail effect that can also induce, let's say a drift in the B direction.
Okay, yeah, I see. But so this is also true of the angular momentum too. All the Poincare charges.
Okay, this is very interesting. No? The angular momentum, I mean, here there are people that are much more expert than me. There is a subtlety that is related to a piece of the contribution. So there would be a similar formula to this one. Let me see if I found it somewhere in my slide. This one. So you see, if you look at this formula, it would indeed seem to be order G cube, right? W times W, W times W, W times W. The issue here is that there is also another contribution in which this W is not really the dynamical waveform I was talking about here. It's really just the total field, and that receives a static contribution. That static contribution has one less power in G, and therefore you get already an order G squared term for the angular momentum. That is, by now has been interpreted in several different ways, but now I think there is a consensus that the true angular momentum that is lost by the binary system, in the sense that it's the object that such that minus that is the variation of mechanical angular momentum, P times B of the massive object is that thing of order g squared. So for the spatial angular momentum. Now I think you were asking about the sort of mass dipole, right? Really the translation that the center of mass experiences. And we had a paper, in our paper with Rodolfo, we were also trying to calculate that thing. So it turns out that it's a bit more subtle in the sense that already at this order g cube, you will start seeing some ambiguity. So in a sense, I think the bottom line of our analysis, what that is also well defined, starts at order g squared, but it suffers it suffers from this time translation ambiguity. Right, so of course that thing will transform if you perform a time translation, because it's well, e times x minus p times t, right? In the Newtonian, so in the non-interacting case, that would be the expression. Of course, you change t to t plus a, it will translate by the radiated momentum. So essentially, it has an ambiguity in the time times radiated momentum direction. So to leading order, only this. So if you want only the J0, let me call this probably X and Y, in order not to use my, so it would be an ambiguity in the Y0 direction, which you can redefine by a time translation in this way, plus PY, sorry, yeah, A0, your by how much you perform a time translation, essentially. So this seems to be the bottom line. I think this is very much related to these issues of infrared divergences, so maybe one could fix this ambiguity by understanding what this log of G is instead of being infinity, right? Maybe it's log of 2Gm over B, at least in the leading order in the mass ratio case, where you can actually solve it non-perturbatively in G, it is 2Gm total mass divided by the impact parameter. Of course, maybe to next to leading order in the mass ratio, the expression inside of log changes, but that is what you should do to fix this ambiguity.
Okay, I think it's time to transition to the next talk. Thank you, Carlo.